Ma'am, shall we wait for 3 more minutes, ma'am?
Yes, yes, of course.
Hello, is it audible?
Yes, ma'am,
Yes.
audible.
Okay, so we are going to start. Okay, so good evening, everyone, and a warm welcome to all the participants joining us today. So, I hope you are having a peaceful and relaxed Sunday. So, to begin today's session with inspiration, here is a meaningful line attributed to Napoleon Bonaparte. The only victories that last are the victories of knowledge. And truly, this FDP supports that spirit, helping us learn, grow, and strengthen our research journey with clarity and confidence. So I need to acknowledge that I was unable to host yesterday's session due to another commitment, and I sincerely appreciate your understanding. It feels wonderful to be back with all of you today. So it's me again, Pradeepa Nagarajan, your host for this evening, joining you virtually and delighted to take you through today's session. So before we proceed, a quick important update need to be said that our day 5 session has now been rescheduled to December 4th as the resource person had an unavoidable academic engagement. So we kindly request all the participants to make a note on of that updated date. So thank you all for your understanding. So before we proceed, a quick moment of silence for today's resource person.
Hello, Pradipha ma'am.
So, to begin today's proceedings with gratitude and clarity, let us join in Jain Mahamantra followed by Tamil Thai Valtu.
ॐ नमो वरिहन्ताणं ॐ नमो सिद्धाणं ॐ नमो यरियाणं ॐ नमो वच्छायाणं नमो लोये सबसाहूणं ईशो पञ्चनमुक्तारो सद्भक्तावपरासनो मङ्गलाणं च सत्त्वेसिं पठमं हवै मङ्गलं पठमं हवै मङ्गलम्
எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறமையந்த செயல் மறந்து வாழ்த்ததுமே வாழ்த்ததுமே வாழ்த்ததுமே.
Thank you all. So, to continue today's program, I now invite Dr. M. Kaveri, who is our convener of this FDP and assistant professor in the Department of Corporate Secretaryship, to deliver the welcome address and to introduce today's esteemed resource person. Ma'am, please.
Thank you, Pradeepa. A very good evening to one and all present here. So this is Dr. Kaveri, Professor and Head, Department of Corporate Secretaryship. On behalf of our department, I am happy and honored to welcome you all in the day 7 of the 10-day International Virtual Faculty Development Program on Research Methodology, Statistical Tools, and Structural Equation Modeling. It gives me a great pleasure to welcome our respected dignitaries, our Secretary, Sri Udan Kumar Chodia, Associate Secretary, Sri Hemant P. Chodia, Dean, Dr. M. Ramya, Deputy Dean, Dr. R. Sureka, and our Director, Dr. N. Venkataramanan, whose presence continues to guide, support, and strengthen all our academic efforts. I'm delighted to extend a warm and heartfelt welcome to our chief guest, Dr. RANIA LAMPOU, STEM instructor, researcher, global academician, educator, ICT teacher trainer, international keynote speaker, author, and global peace ambassador in Greece. It gives me great excitement and pleasure to introduce today's chief guest, Dr. RANIA LAMPOU. She currently serves at the Greece Ministry of Education in the Directorate of Educational Technology and Innovation. She also works as a STEM instructor at the Greece Astronomy and Space Society. She has received more than 200 national and international awards. She is the winner of the Global Teacher Award for 3 consecutive years, 2020, 2021, and 2022 by AKS Awards, and was a Global Teacher Prize finalist 2019 by the Varkey Foundation. She has been recognized as a global icon 2020 in Passion Vista magazine, listed among the top 10 women entrepreneurs in Fortune, featured among the 100 most successful women in business in an Amazon book by the Global Trade Chamber, and included among the top 10 CEOs of the year 2021-22 by DigiShocks and Indian Alert. She is also featured in several international publications, including 30 Shining Stars of the World, Hayden's Book 2023, Queen's Book 2021, 22, 23, and 24, and Hoinser Global Women Book 2023 by the Hoinser Media Group. Rania is the founder and the international coordinator of numerous innovative global projects aligned with the United Nations Sustainable Development Goals. She is also the author of scientific books for children and collaborates extensively with international organizations, having delivered more than 3,500 lectures and training sessions at international platforms. She continues to influence educators worldwide. She is a committed social activist and a member of the educational committee of the Unimical Delphic Union and in collaboration with Harvard University. She has earned several humanitarian and peace awards from international humanitarian organizations for her contributions. In addition, she serves as an editorial board member for multiple academic journals and has presented research in numerous international conferences, also published extensively in reputed journals. We are truly honored by your gracious presence and eagerly looking forward to your insightful contribution. Welcome, ma'am.
Thank you so much for the beautiful introduction. Warm greetings from Greece, from here from Athens. And
Yes,
very,
ma'am.
very honored and very excited to be invited to this very, very precious faculty development program. And I would like to extend my heart congratulations to all organizers of the Department of Corporate Secretaryship, Group Head Manuel Jen College. And of course, I would like to thank you for the kind invitation. Before starting sharing my presentation, I would like to just to highlight that it's my great pleasure to welcome you all to this session, which focuses on 3 pillars of strong scientific inquiry: reliability, validity, and multivariate analysis. And today, we come here not only to explore the statistical concepts, but also to strengthen the very foundation of how we understand, we interpret, and improve the world through research. Because reliability reminds us that good research must be consistent. Validity challenges us to go deeper, asking whether we are truly measuring what we tend to measure. And together, they ensure that our findings are trustworthy, credible, and meaningful. Multivariate analysis, in turn, invites us to embrace complexity because it acknowledges that real-world phenomena rarely stem from a single factor. By examining multiple variables at the same time, we gain richer insights, we uncover hidden patterns, and make more informed decisions. In a world overflowing with data, multivariate analysis empowers us actually to transform information into knowledge. And we want to explore also the role of AI here, what amazing tools we can leverage, because AI plays a powerful role in advancing all these pillars. And why? Because it enhances reliability by reducing human error and improving measurement precision. It strengthens validity by enabling sophisticated data processing, pattern detection, simulation techniques that help us better understand what our instruments indicators truly capture. And through advanced machine learning models now, AI expands the possibilities of multivariate analysis, allowing us to handle large data sets, explore complex relationships, and generate predictions with unprecedented accuracy. And I want to say here to share that we have the first AI school in UK. It was the last year, which works on a pilot basis. We talk about teacher-led school. The first AI university in India, I think in Kerala, was established. So AI is here, and we need to embrace it, of course, wisely, responsibly, and ethically. So thank you all for being here. And now we'll start sharing a presentation. It's a huge chapter. We'll try to stick to the time because I have a lot to say today to share. I don't know if it's visible now.
Yes, ma'am, visible, ma'am.
Yes,
Can you see also the change of slides?
yes, ma'am.
Okay, thank you. So in research measurement, very briefly, just remind you that reliability refers to the consistency, stability, and repeatability of a measurement instrument. So a measure is considered reliable if it produces the same results under consistent conditions. So key points here is consistency, that the instrument yields similar results when repeated to the same population. Results remain stable over time if what is being measured has not changed, and dependability, the measurement is free from random error. Some types of reliability, test-retest when consistency of scores over time, inter-rater reliability, the degree of agreement between different observers or raters, and the internal consistency, extent to which items on a test measure the same concept. So in short, we could say that the reliable instrument gives trustworthy results, but it must also be valid to measure what it intends to measure. So some differences between them. Reliability, it's consistency or stability. We said before, so the focus here is precision and repeatability. What we ask, does the instrument measure the same way every time? Validity refers to the accuracy of the measurement tool. And of course, here the focus is correctness and relevance. Remember that the tool can be reliable but not valid. For example, consistently gives the wrong result. A tool cannot be valid unless it is reliable, because inconsistent results cannot be accurate. Internal consistency now. Internal consistency and stability in the context of reliability. What is happening here? This is how well the items on a test measure the same construct. So if all items are supposed to assess the same underlying trait, for example, anxiety or math ability, they should be correlated with one another. So key ideas here is that it checks the homogeneity of items within a single tester. High internal consistency means that the test items work together to measure one concept, and it is usually estimated in one testing session, not across time. Common measures is compact alpha, the most widely used, the split half reliability, we're going to explore this today, and Kuder-Richardson formulas. What about stability and reliability? This refers to the consistency of scores over time. So if the same individual takes the same test again after a period of time, then the scores would be similar if the constant being measured has not changed. So here the key idea is that stability measures test retest reliability. High stability means the test is reliable across repeated administrations, and it is useful when the characteristic measure is expected to remain steady. For example, intelligence or personality traits. How it is assessed? Usually with a test-retest method, so administering the same test to the same group twice and correlating the scores. So internal consistency, we ask, do the items within the test agree with each other? And stability, what we ask, do the test scores stay consistent over time? So this test-retest refers to the consistency of a measurement instrument when the same test is given to the same group of people at two different points in time. And of course, here we assume that the constant being measured has not changed. So it evaluates the ability, the stability of the measurement over time. For example, a researcher gives a stress questionnaire to a group of employees on Monday. 2 weeks later, the same questionnaire is given again to the same employees under similar conditions. If the scores from time 1 and time 2 are highly correlated, then the questionnaire demonstrates high test-retest reliability. When this should be appropriate, usually we could say that when the constant naturally changes quickly, and when we take the test, when taking the test once affects how people respond the second time, for example, knowledge tests or problem-solving tasks where participants may remember previous questions. When the second administration could cause reactivity on learning, for example, attitudes that may shift simply because participants reflected on them after the first test. And when external conditions cannot be controlled between test sessions, for example, measuring pain levels in patients whose medical condition may fluctuate. And now, I mentioned about inter-rater reliability. It's the degree of agreement between two or more observers or raters who assess or score the same event or behavior. So here it indicates how much homogeneity or consensus there is in the ratings given by different individuals, and how this is assessed through percent agreement. Is the simplest method, which calculates the percentage of times the raters agree out of all ratings. Cohen's kappa, which is used for two raters, it adjusts for chance agreement, making it more accurate than percent agreement, and is suitable for categorical data also. Place kappa, an extension of Cohen's kappa, used for 3 or more raters. In the intra-class correlation coefficient, it is suitable with 3 or more raters. It is used for continuous data. And Krippendorf's alpha, which works with any number of raters that can be used for different types of data. It's useful when data are missing or raters vary. Now, what about split half reliability and how this works? This is a method which is used to assess the internal consistency of a test. In other words, how well the tests on the test measure the same concept. So it actually involves splitting the test into 2 equal halves, and then we correlate the scores on both halves. If the 2 halves produce similar results, then the test is considered reliable. Here you can see how this works. A single test is given once to a group of people. Then the items in the test are divided into comparable halves. For example, the odd and the even items. Each person gets 2 scores, and the correlation between the 2 sets of scores is calculated. A higher correlation means higher split half reliability, because each half is shorter than the full test. A correction formula, Spearman-Brown's prophecy formula, is often here used to estimate the reliability of the full-length test. An example here, imagine that we have a 20-item math achievement test, which aims to measure arithmetic skills. So the first step is to to split the items into odd and even numbers. Then the student takes the full test and scores odd items like this and even items like this, and the teacher calculates then the correlation between the odd item scores and even item scores across all students in the class. So if the correlation is high, then this means that the two halves of the test measure the same ability. If we apply what I mentioned before, the Springer-Brown correction, the estimated reliability of the full test might be even higher. In simple terms, split half reliability checks whether half of the test agrees with the other half, ensuring that the test items are consistent and measuring the same thing. We all know about Cronbach's alpha, which define actually internal consistency and how well actually the items on a test or a questionnaire measure the same underlying construct, and how usually this works. Actually, it measures inter-item correlation. It considers the number of items, of course, based on variances, and it produces a coefficient 0 to 1. So if I say, for example, that a scale shows a Cronbach's alpha, how we can interpret this? Then we can say that these items do not reliably measure the same underlying constant, because we need to have in mind the scale that is mentioned here. For example, 0.5, this proves that we have a poor range. So here, since we have a poor range, the scale likely needs revision. So what we can do in this case, we can remove unclear or poorly correlated items, or we can rewrite items for clarity, or we can add better items that represent the construct. Some practical strategies to increase reliability in our data collection. First, we need to standardize procedures. We can use, for example, the same instructions, environment, and timing for all participants. For example, you can administer all surveys in a quiet room under similar lighting and time constraints. Use clear and precise instruments. Ensure questions or test items are unambiguous, so easy to understand. Avoid double-barreled questions, so asking two things at once in surveys. Train data collectors. Make sure that all researchers, interviewers, or observers follow the same protocol. Example, we conduct mock sessions to provide a detailed manual. Increase the number of observations or items. So more items in a test or more observations in measurements often improve reliability. For example, a longer questionnaire on stress will capture the construct more consistently than a very short one. The pilot testing, when we conduct a small-scale trial before full data collection to identify issues with questions, equipment, or procedures, and by using reliable instruments, so choosing here established scales or measurement tools with proven reliability rather than created and tested ones. Control external factors, or minimizing environmental and situational variability that could affect results, temperature, noise, and things like that, which could affect the responses. And of course, repeating measurements for constructs expected to remain stable. We measure more than once and we check consistency over time. Randomizing or counterbalancing, so reduce order effects or fatigue by randomizing questioned item order when this is applicable. And consistent scoring, we use clear scoring criteria, possible with multiple raters. For example, for a seat rating, we can provide a rubric and have two graders score independently, and then check in the rater agreement. And now, when should a researcher consider removing items in order to increase reliability? When an item has very low or negative item total correlation. Items that don't correlate with the overall scale likely do not measure the same underlying construct. A negative item total correlation usually signals what? It signals a reverse-coded wording that wasn't actually reversed or a fundamentally consistent item. The alpha, if item deleted, drastically increases. If deleting an item substantially improves reliability and the item is conceptually weak or outdated or unclear or off construct, removal might be justified. If the items show poor factor or loadings in factor analysis, so if these items with low factor loadings or cross loadings may not measure the intended latent variable, if the item shows poor performance across multiple validity checks, not interpretable by respondents or ambiguous or double-barreled wording, etc., and when the item contradicts theoretical coherence of the scale, even if reliability increases, a conceptually irrelevant item does not belong in the scale. In these cases, we can remove items. When we should not remove items, reliability increases with more items. Removing items simply to boost alpha can distort the construct. So when we increase alpha artificially, when we remove theoretically essential items, even if an item reduces alpha slightly, it may be needed to cover the domain of the construct. Removing items without checking the dimensionality first, low reliability might signal multiple dimensions, not bad items. So what is the best practice here is to conduct both conceptual review statistical diagnostics, try to check and inspect the item total correlations, inspect factor analysis, consider theoretical coverage of the construct, and document reasons transparently. Pilot testing also is important. It can improve reliability. How? Because it helps reveal confusing items. Participants in a pilot may interpret questions differently than intended, which lowers reliability. So fixing a clear wording increases consistency. It identifies technical issues, problems in instructions, in timing, or administration procedures. This can lead to inconsistent responses. A pilot always allows refinement of these procedures. It allows assessment of internal consistency because researchers can do what? They can calculate reliability statistics using the pilot data to see which items perform poorly or highlight items that do not correlate well with others. Problematic items then can be revised or removed to strengthen the overall scale. Improves training protocols definitely, because if data collectors misunderstand procedures or apply them inconsistently, then pilot testing reveals this, so training can be improved. Ensure stability over time. Test reliability can be checked with a pilot in order to ensure measurements are consistent across occasions. So pilot testing helps refine instruments, instructions, and procedures, leading to more consistent and reliable measurements in the final study. And also another issue here, just a quick reminder that environmental conditions play a critical role in the reliability of systems and components and instruments observed in field studies. Unlike controlled laboratory settings, field environments introduce variable, unpredictable interactive stressors that can significantly influence performance and failure rates. So be careful of the temperature, the humidity and moisture, the mechanical stressors like vibration, the solar radiation, chemical, biological agents, the impact on data quality, because environmental fluctuations can produce many failures, making malfunction diagnosis challenging. And some mitigation strategies here is, in order to maintain reliability in field studies, what we can do is to use weatherproof equipment, for instance, or apply protective coatings and corrosion-resistant materials. We can implement environmental controls, for example, enclosures or insulation, or we can conduct environmental qualification testing, thermal cycling, etc., and regularly calibrate and maintain equipment. So environmental conditions introduce complex real-world stressors that significantly affect the reliability in field studies. Understanding and planning for these influences is essential to ensure credible data, operational continuity, and of course, more reliability. Some AI tools for checking reliability are SPSS plus AI plugins, GSP with AI, of course, plugins, and of course, JMOV, it's very popular, Google Colab, Jupyter, Python assistants, etc. I don't know if you are familiarized with AI tools, but we will see later also some other tools. Now, what about validity. Validity already mentioned some things that this refers to the extent to which a measurement instrument measures what is intended to measure. So the key points here is accuracy. Validity focuses on the truthfulness of the measurement. It ensures that the results reflect the intended concept, not something else of relevance. And of course, even a reliable instrument can be valid if it doesn't measure the right thing. We have different types, very briefly, because I want to focus more on multivariate analysis. Whether the measurement covers all aspects of the concept, then we have concept validity. Concept validity, whether the test truly measures the theoretical construct it claims to. For example, a depression scale actually reflects depressive symptoms, not general stress. A criterion-related validity, how well the measurement correlates with an external criterion. And this includes predictive validity, when we predict future outcomes, and confidence validity, which correlates with a current standard. For example, a new blood test compared to an established lab test. So accuracy, meaningfulness of the measurement, a valid instrument measures the intended concept correctly. And you mentioned before about the differences between reliability. The first one, the focus is reproducibility and precision of results. Here, the focus is truthfulness and correctness. So how can a researcher improve construct validity in a study? By clearly defining constructs, by using multiple measures is another strategy, and ensuring content relevance, avoid confounding variables, and of course applying statistical techniques. Some threats to external validity in experimental research. Here we can start by the history, and of course then we have the maturation, the testing, and these threats must be under our control, of course. We need to know before about them so we can be ready. Instrumentation, the statistical regression, selection, experimental mortality, as we say, and finally, interaction effects. So here, what I want to say that events outside the experiment that occur between pre-test and post-test may affect the outcomes. This is the history. Maturation, changes within participants over time that affect results. The act of taking a test may influence future performance. So this is the testing. Then instrumentation, changes in measurement tools or observers, so we score methods during the study. The statistical regression, extreme scores tend to move towards the mean on subsequent testing. For example, participants with unusually high pre-test scores may score lower on post-test regardless of the intervention. Enter selection, because systematic differences between groups that affect outcomes is another issue. If participants self-select into treatment and control groups, then inherent differences may confound results. Experimental mortality, when we have lots of participants, interaction effects, the combination actually here of threats. So threats to internal validity reduce definitely confidence that observed effects are truly caused by the independent variable. So what we need is careful experimental design, like randomization, control groups, standardized procedures that can help minimize these threats. So clearly defined constructs provide a precise operational definition of the concept being studied, how we can improve the construct validity in a study, by employing different methods to measure the same construct, so triangulation, by making sure that the measurement covers all aspects of the construct, the content validity, by controlling for external factors that could influence the measurement, so avoiding confounding variables, by testing instruments on a small sample to detect ambiguities or biases before full-scale research, And of course, by incorporating validated scales with proven construct validity in order to increase reliability and comparability. And finally, using factor analysis to confirm that items on a scale load onto the intended construct. So check correlations with related constructs, what we call convergent validity, and unrelated constructs discriminant validity. So if we want to improve construct validity, it's about clear definitions, comprehensive measurement, control of confounds, and rigorous testing in order to ensure that this, what is being measured truly represents the intended concept. And of course, here we have the subject matter experts, and what role they play in validity assessment. They actually review items in order to ensure they cover all important aspects of the construct without including irrelevant material. So they help define whether each question or task aligns with intended learning outcomes or skills or behaviors. They check the language terminology, so they ensure the clarity and appropriateness. By reviewing the conceptual framework, they help confirm that items truly measure the underlying construct and not the unrelated factors. And they often provide feedback on whether the test content aligns with the theoretical expectations. They can advise on the relative importance on different content areas, and their input is used also in pilot testing and revisions, improving the overall validity of the instrument before it is widely used. So these subject matter experts, that what they do, they ensure that the test or an instrument is accurate, is representative, is meaningful by applying the deep knowledge of the subject area. Because without their input, even statistically sound assessments might fail to measure what they are intending to. How now a nomological network used to establish construct validity. So this is another issue here. What is nomological network? Is a conceptual framework that shows how a construct relates to other constructs and observable measures based on theory. What I could say, it's a key tool. It's a tool for establishing construct validity, which is about whether a test truly measures the intended theoretical concept, how it works. First, we clearly specify what is the construct. For example, the construct is job satisfaction. Then the network includes theoretical relationships, convergent constructs. For example, this should correlate strongly with your construct. For example, job satisfaction and organizational commitment. If we have discriminant constructs, this should correlate weakly or not at all. For example, job satisfaction and physical fitness. Then we map observable indicators, show how each construct is measured by specific items, scales, or behavioral indicators. We specify expect relationships, so use theory to predict direction and strength of correlations among constructs, and test empirically, collect data, check whether the observed relationships match the predictions, and check about the convergent and discriminant validity. So why it establishes construct validity, this nomological network? Because a construct is valid if it behaves as expected within the nomological network, and actually it links theory, measurement, and empirical evidence showing that the construct is not just measurable but meaningful in context. An example here, you have, for example, organizational commitment. Here is a construct. Strong positive correlation is convergent, work engagement, moderate positive correlation, physical fitness is discriminant, no correlation at all. If a construct is turnover intention, then we have strong negative correlation, so predictive. What would say it's essentially a map, I could say, map of theoretical expectations, because construct validity is demonstrated when the observed patterns of relationships among constructs indicators match the predictions into the network. The multi-trait and multi-method matrix for assessing validity. This is another framework which was introduced by Campbell and Fiske, and aims to assess the construct validity also. It combines multiple traits and multiple measurement methods in order to separate true construct effects from method-related bias. So here, the construct will have the constructs, the actual characteristics or psychological constructs that are being measured, for example, anxiety or motivation or anything else. We have the methods, different ways of measuring the same characteristic, and matrix structure, which is a table showing correlations between all measures. And we will have diagonal show correlations of the same trait measured by the same method, so should be high. And off diagonal, this shows correlations of different traits of different methods. How we can assess the method with this matrix? The convergent validity. So these measures of the same trait using different methods should correlate highly. For example, self-reported anxiety and observed anxiety should be strongly correlated. Discriminant or divergent validity, when measures of different traits should have low correlations even if measured by the same method. For example, anxiety and intelligence measures should not correlate strongly. And method effects, when correlations between different traits are measured by the same method, this can actually indicate method bias. And helps identify also if high correlations are due to the characteristic of the method used. So here is one example of this. And the role of hypothesis testing is very, very, very important in evaluating construct validity, because it provides a systematic method to assess whether a test or measurement instrument accurately reflects the theoretical construct it is intended to measure. Construct validity, it's about whether the operationalization of a construct truly captures the underlying concept. And hypothesis testing offers here empirical evidence for or against that. So linking theory to observations, so construct validity begins with a theoretical definition of a concept. Hypothesis allows researchers to derive specific testable predictions from the theory. Then we test relationships between variables. And hypothesis testing evaluates whether empirical data support the expected patterns predicted by theory. Hypothesis then about factor structure, number of dimensions, which items load, or which factors are tested using confirmatory factor analysis. The experimental group differences, hypothesis testing then can evaluate construct validity by examining predicted differences between known groups. And the role, of course, in a third validation, hypothesis testing is not a one-time check, but part of an ongoing validation process. So theory suggests a pattern of relationship, hypotheses are formulated, data collected and tested, and results either support, refine, or challenge the construct and its operationalization. Limitations, because passing the hypothesis test does not prove construct validity, it proves evidence in support of it. Remember this, and multiple convergent and discriminant tests across contexts strengthen validity evidence. So hypothesis testing allows researchers here to empirically examine whether measures behave as theoretically predicted, test the convergent and discriminant relationships, they validate the factor structure of scales, and examine group differences consistent with the structure. By systematically comparing observed data to theoretically derived expectations, hypothesis testing provides quantitative evidence supporting or challenging the validity of a construct. Some tools for evaluating validity: SMART, PLS, MEOS with AI-based interpretation scripts, so statistical AI platforms. For writing ELISIT, actually for the whole research design, we have a wide range, if I can give you the whole list at the end. But now we talk about validity. Python or R for factor analysis and CMM model evaluation, etc. I'm going to see other tools also. So how do reliability and validity influence the choice of statistical techniques? Because here, if we talk about high reliability, then this supports the use of parametric tests in NOVA because assumptions about stable measurement are more likely to be met. For low reliability, you may need techniques that account for measurement error, such as structural equation modeling or composite scores with error correction. And of course, about validity, high validity allows interpretation of statistical results, supports confirmatory analysis, to test theoretical relationships. If we have high validity, but if we have low validity, we may require exploratory techniques first in order to understand what the items actually measure, because we risk to give misleading results. The influence of specific statistical choices, high reliability in terms of factor analysis, what is happening in NOVA, we're going to see about this now. So in terms of correlation, the high reliability is appropriate, and low reliability, you can understand that it's low. So key points: reliable data reduces power, increases type 2 error. Invalid data, we have results that may be statistically significant but meaningless. Latent variable methods are preferred when reliability issues exist, and always check for reliability and evaluate reliability and validity first, because poor psychometrics can give a more exploratory or error-correcting approach rather than standard parametric tests. Now, what about multivariate analysis? This is a set of statistical techniques which is used to analyze more than two variables at the same time in order to understand relationships, patterns, or effects among them. So it actually helps researchers examine complex phenomena where multiple factors interact. It involves three or more variables. It can explore relationships, predict outcomes, and some common techniques: multiple regression, ANOVA, factor analysis, structural equation modeling, cluster analysis, principal component analysis, and discriminant analysis. Why multivariate analysis is important in modern research? Because it allows researchers to examine multiple variables at the same time and understand complex relationships that cannot be captured by simple one variable at a time analysis. So why this? Because real-world phenomena are usually influenced by multiple factors. This is a fact. For example, academic performance depends on intelligence, motivation, socioeconomic status, etc. Multivariate analysis can consider all these variables together. Second, it shows how independent variables jointly affect the dependent variable. It helps detect correlations, interactions, or patterns that univariate or bivariate analysis might miss. Third, it allows adjustments for variables that could distort the observed relationship. For example, controlling for age and gender when we study the effect of exercise on blood pressure. It improves prediction accuracy because multivariate analysis like regression or factor analysis or structural equation modeling provide better predictions than single variable models. It facilitates dimensionality reduction data simplification because techniques like principal component analysis or factor analysis reduce large data sets into key components, making patterns easier to interpret. And it supports advanced research design because this is essential for longitudinal studies, for experimental designs with multiple treatments, or survey data with many variables. Therefore, multivariate analysis allows now modern researchers to analyze complex, interrelated variables, control for confounders, and make more accurate inferences and predictions reflecting the complexity of real-world phenomena. Sample size is important in multivariate techniques because these techniques actually analyze multiple variables at the same time and often rely on statistical assumptions that require sufficient data to produce reliable, stable, and valid results. So multivariate techniques like multiple regression, for example, or MANOVA, estimate multiple parameters at the same time. A larger sample size reduces the standard errors of these estimates, leading to more precise and trustworthy parameter values. For statistical power, power is the probability of correctly detecting the true effect. Small sample sizes can lead to low statistical power, increasing the risk of type 2 errors, and failing to detect significant relationships among variables. The stability of covariance or correlation matrices, because many multivariate methods depend on the covariance or correlation matrix of the variables. With small samples, these matrices can be unstable, poorly estimated, or even singular, non-invertible, which can make techniques like factor analysis or regression unreliable or impossible to perform. Assumption of normality, techniques like MANOVA, for example, and discriminant analysis assume multivariate normality. Larger samples help satisfy these assumptions through the central limit theory, making test statistics more robust and valid. And model complexity, here, we can see that in multivariate techniques, what is happening? The number of parameters grows quickly with more variables. So a small sample relative to the number of variables can lead to overfitting, what we call multicollinearity, or models that cannot converge. The rule of thumb here is that many techniques suggest at least 5 to 10 observations per variable, though more may be needed for complex models. Generalizability of results. A large sample better represents the population, improving the external validity of findings. Small samples may produce results that are specific, sample-specific and not replicable in other populations. So, in brief, sample size multivariate analysis is crucial because it ensures precise estimates, reliable statistical tests, stable covariance structures, and valid generalizable results. Insufficient sample size can lead to misleading or invalid conclusions. And how can multivariate analysis be used to validate survey instruments? This is extremely useful for survey instruments because it allows researchers to examine the relationships among multiple survey items at the same time, assess underlying constructs, and ensure that the instrument measures what is intended to measure. For example, exploratory factor analysis uncovered the underlying structure of a set of survey items without pre-specified assumption. The confirmatory factor analysis helps to test whether a hypothesized factor structure fits the data. The reliability analysis using multivariate correlations, the purpose here is to assess internal consistency and stability of survey scales. So how it validates instruments, Cronbach alpha or composite reliability is computed from correlations among items, or multivariate analysis can show if some items reduce reliability, indicating that they may not belong to the intended construct. What I mentioned before about discriminant and convergent validity, to ensure that constructs are distinct yet related as theory predicts, and multivariate regression. The purpose here is to examine relationships between constructs or between constructs and outcomes. So how this validates instruments? If the instrument measures the intended construct, then this construct should predict relevant outcomes logically. And this also confirms criteria-related validity predictive of concurrent. So multivariate analysis validates survey instruments by identifying latent constructs, testing hypothesized measurement models, assessing internal consistency by confirming convergent and discriminant validity, and of course by ensuring constructs relate appropriately to outcomes. And why is measurement quality crucial before performing multivariate analysis? Because the reliability and validity of our measurements directly affect the accuracy, interpretability, and trustworthiness of the results. Poor measurement quality can lead to misleading conclusions, even if the statistical techniques are applied correctly. So this ensures reliability. Multivariate analysis assumes that the variables are measured consistently. Unreliable measures increase random error, which can attenuate correlations and reduce the power to detect real effects. Of course, this maintains validity because validity ensures that each variable accurately represents the intended construct, prevents bias. Poorly measured variables may introduce systematic error, distorting parameter estimates and misleading conclusions about relationships among variables. It supports interpretability. High-quality measurements make the interpretation of results straightforward. For example, in a factor analysis, poor measurement quality can obscure the underlying factor structure. It improves statistical power. Accurate and precise measurements reduce noise, increasing the ability of multivariate tests to detect the true relationships. It is critical for complex models also, because multivariate analysis often rely on assumptions like linearity, normality, and homoscedasticity. So measurement error can violate these assumptions, leading to incorrect statistical inferences. Multiple regression analysis, this is technique which is used to examine the relationship between one dependent variable, the outcome, and two or more independent variables, the predictors. So here we have predicting outcomes, which allows the researcher to predict the value of a dependent variable based on several dependent variables. For example, predicting a student's final exam score based on our studies, attendance, etc. It helps assess the relative importance of predictors, control for confounding variables, understanding relationships, and modeling complex phenomena. Multiple regression analysis like asking how do all these factors together affect this outcome and which one matters most. It's like this. And what assumptions are required for multiple regression? In order to ensure valid results, here we need to have linearity because the relationship between the dependent variable and each independent variable is linear. So check with scatter plots or residual plots. The dependence of errors, observations are independent, residuals are uncorrelated, so violation may occur in time series or cluster data. What we call homoscedasticity, when the variance of residuals is constant across all levels of the dependent variables. Heteroscedasticity, which is unequal variance, can bias standard errors. The normality of errors, what is needed, because residuals should be approximately normally distributed, especially important for small samples to ensure valid hypothesis testing. The no multicollinearity, because independent variables should not be highly correlated with each other. High multicollinearity inflates standard errors and makes it hard to interpret coefficients. It can be checked through variance, inflation factor, etc. And no significant outliers on conventional points. Extreme values can distort the regression coefficient, etc. So this assumes linear, independent, homoscedastic, or normally distributed errors with no multicollinearity and minimal outliers. Violating these assumptions, this can lead, of course, to biased, inefficient, or invalid results. The logistic regression, here is a statistical method which actually used to model the relationship between one or more independent variables, predictors, and a categorical dependent variable, typically binary. So unlike linear regression, which predicts a continuous outcome, logistic regression predicts the probability of an event occurring. How it works like this. The dependent variable is binary. Logistic regression models the log odds of the probability of the event occurring like this. The logging function transforms probabilities to the real number line, and this helps with linear modeling. The model estimates coefficients that indicate predictors affect the log odds. And this, what the characteristics that this can handle continuous categorical mixed predictors. It can be extended to multinomial, more than two categories, or our ordinal logistic regression. So we could say that this is, it has many applications also. In medicine, for example, when we want to assess treatment success probability, when we want to predict disease presence, in social sciences also, when we want to predict the student dropout. in business. So it's a versatile tool for predicting binary outcomes and understanding the influence of predictors on the probability of an event. Its interpretability through odd ratios makes it popular across medicine, social sciences, business, and finance, because here you can see we have outputs, odd ratios, which show how a one unit change in the predictor affects the odds of the outcome. MAINOVA, very popular. First, we have the ANOVA, which is the statistical technique which helps define whether there are significant differences between the means of two or more groups. Here we have only one dependent variable is analyzed at a time, and one or more categorical dependent variables or factors. With MAINOVA, the purpose is here to test whether the vector of means of multiple dependent variables differs across groups. So in terms of dependent variables, we can have two or more dependent variables, which are analyzed at the same time. And independent variables, which is similar to ANOVA, one or more categorical independent variables are there. So the key differences are, I think, very evident in terms of purpose, in terms of sensitivity to correlations, etc. The structural equation modeling, this is a statistical technique which used to examine complex relationships among observed and unobserved variables. So it combines aspects of factor analysis and multiple regression. This allows researchers to test theoretical models that specify causal relationships and between variables. And what is the key features? We have latent observed variables at the same time with simultaneous equations, model testing, causal modeling. And the role of Cronbach alpha in structural equation model is that before modeling, you check whether the items intended to measure a latent construct are internally consistent. So high Cronbach alpha ensures that indicators reliably reflect the latent variable. So it helps, Cronbach alpha helps assessing the reliability of latent constructs. Second, it helps guide measurement model validation. So this consists of a measurement model and a structural model. The structural equation modeling consists of both measurement and structural model. So Cronbach alpha used here in the measurement model stage to ensure that each latent construct is measured reliably before analyzing relationships among constructs. Complementing other reliability measures. While structural equation modeling uses composite reliability and average variance extracted for latent variables, Cronbach alpha actually provides a preliminary check of internal consistency. If Cronbach alpha is low, it signals that some items may need revision or removal. And some limitations in this same context is that Cronbach alpha assumes that all items contribute equally, which is often unrealistic in structural equation modeling. This CEM often prefers composite reliability, which accounts for different factor loadings. Therefore, Cronbach alpha is mainly used as an initial reliability check, not the final measure. So what is the summary here? That the purpose is here to evaluate internal consistency of indicators measuring latent construct. The role of Cronbach alpha here is to ensure measurement reliability before testing structural relationships. And the caution is that this should be complemented with CEM specific reliability measures. The eigenvalues in factor analysis, very briefly, these are a key concept in factor analysis, which is a statistical technique used to identify underlying relationships, factors among a set of observed variables. So these eigenvalues represent the amount of values or the amount of variance in the observed variables that is explained by a particular factor. Higher eigenvalue factor explains more variance. lower eigenvalue. Factor explains less variance. So mathematically, eigenvalues come from the correlation or covariance metrics of the observed variables. Each factor corresponds to an eigenvector, and each eigenvalue tells us how much the total variance is captured by that factor. Factor analysis involves decomposing the correlation matrix into factors, and each eigenvector represents a factor. Each eigenvalue tells us the variance explained by that factor. And interpretation factor analysis, as you can see, it has a criterion, the screen plot, etc. So the summary here is that eigenvalues quantify how much variance each factor explains. They help decide how many factors to retain the model, and eigenvalues are derived also from the correlation or covariance matrix of the data. And remember some ethical practical challenges. Of course, we need to be aware when we conduct any research about informed consent, about the privacy, use also the data. Participants should know, should be aware of what data will be used, how they will be used in the research. Cultural sensitivity, and of course the practical challenges which are related with measurement complexity, the subjectivity of responses, the sampling issues, the resource constraints, and so on. How we can balance ethics and practicality by using pilot testing to identify potential issues before large-scale data collection, apply anonymization in situ data handling to protect privacy. Very useful triangulation, always multiple measures in order to enhance our validity, and of course, implement cultural adaptation and sensitivity check for instruments. Some AI tools we can use. AI enhanced statistical software, IBM, PSS, with AI-assisted features. MP Pro, which offers interactive visual statistics and machine learning integration. As machine learning platforms with Autostats, RapidMiner, it's very popular. Data robot to analyze variable importance. The AI-assisted Python environment, Jupyter Notebooks with AI plugins, it's a generated code for Innova, MyNova, mixed effects models, the Google Colab and extensions, AI-driven data assistants, Microsoft Copilot, and AI-powered visualization tools, very popular, Tableau with AI, Power BI, I guess we are all familiarized with this. AI-oriented statistical libraries, Penguin, Python, stat models, are with AI assistants, and in general, how will AI shape the future of multivariate statistical research with automated model discovery, variable selection, because especially deep learning and symbolic regression will automate large parts of model search. Definitely, by automatically detecting nonlinear relationships, higher-order interactions, by suggesting optimal transformations, by performing explainable dimension reduction. We will have new forms of dimension reduction because traditional models now are being augmented by AI supervised embeddings that maintain interpretability, more generative representative learning that produce lower dimensional structures with uncertainty estimates. The unified statistical machine learning workflows, which show that statistical research will increasingly degrade now probabilistic programming languages that incorporate classical covariance structures or machine learning pipelines that automatically enforce statistical assumptions, and Bayesian neural networks with multivariate posteriors. This produces end-to-end systems that run multivariate modeling with less human intervention, but better diagnosis. Simulation-based inference, massively now AI accelerates high-dimension, what we call Monte Carlo methods, and synthetic multivariate data generation for rare events, bootstrapping of complex multivariate estimators, and this expands what's practically inferable in high-dimensional spaces, and of course, causality in high dimensions, because causal inference, once it's limited by dimensionality, is benefiting from AI-guided causal discovery algorithms by scalable conditional independence tests, by hybrid causal ML models enabling multivariate treatment effect estimation. AI is black box. Black box, we know that's the major challenge of machine learning because we don't know how the systems jump to conclusions. We don't know the inner processes of these conclusions. So black box has created a new era where multivariate statistics is vital. We expect new statistical theory about explaining non-linear multivariate models with guarantees. AI systems will auto-write statistical code made in the future, verify assumptions, but detect modeling mistakes, generate reports with diagnostics. Already this is happening, and this lowers the barrier to high-level multivariate analysis, while statisticians now focus on theory, interpretation, and validation. A new theory emerging because AI acts now as an empirical engine for discovering statistical structure, etc. So AI won't replace multivariate analysis, multivariate statistics definitely, but it will expand it, providing that new tools for high-dimensional exploration, automated workflows, new theory driven by complex models, and more scalable and expressive ways to understand relationships among many variables. So before concluding, I had the two activities in my mind, but I think there's no time for this. If some new psychological skill shows high reliability but poor predictive validity, how we can explain this? We start by explaining the reliability, consistency, or stability of a measure. A test reliable if it gives similar results under consistent conditions. Then about validity, then if a psychological skill is highly reliable, it consistently measures something, but it has poor predictive validity, it fails to predict the outcome it was intended to predict. Then we say that the test is consistent. We check for possible reasons that would be constant mismatch, item issues, criterion selection, the outcome variable chosen for prediction may not align with a constant measure, or overly narrow focus. A reliable test is necessary, but not sufficient for predictive validity. You need both consistency and accurate alignment with the criterion. And there was another activity. Okay, we don't have time now. If, for example, a researcher here developed a motivation scale, describe steps to evaluate its reliability and validity. Then we start for the main linear steps. We define the construct clearly, we generate the items, then we ensure the reliability, maintain consistency, test, retest, we have reliability, and we evaluate finally the validity through content validity and the construct validity, exploratory factor analysis, confirmatory factor analysis, the criteria related validity, refinement, finally how we need to remove, for example, items with low reliability, revise items, or reassess reliability. Finally, report to compass alpha, test, retest reliability, factor structure, etc. So thank you very much for your attention. And of course, the ethical challenges, as I mentioned before, are very important. For any question, I'm here to discuss. Sorry for delaying. Okay.
Pradeepa ma'am?
You can write to the chat box also.
Yes, ma'am. Ma'am, thank you very much for such a informative and valuable session. Your presentation was so clear and engaging and also very helpful for all of us. So, ma'am, before we move on, so I'd like to take a brief moment on behalf of all the participants to say your credentials and contributions in the field of education and research are truly commendable. So, we are honored and grateful to have you with us today. Good. So, and now, so if I may ask something a little lighter, since you are joining us all the way from Greece, we are curious. So, how is the weather there right now? And what would you say is the best time of the year to visit Greece? So, not going to visit, but
Okay,
still,
yes.
if by chance.
Okay, now we have a very soft, I could say, winter, warm winter,
Okay.
but the best time is the summer. Summer here it starts with June, July, August.
Okay.
But I want to say that I'm planning to visit India in April. I will stay 2 weeks in Chennai because I'm involved in a space program of ISRO. and the Space Kids India, and I will come with Greek students. And it's fantastic because we're going to build mini satellites, CubeSats, which will be sent to the moon in the next historical space mission, Chandrayaan-4. You know very well, better than me, the Chandrayaan-3 space mission, which was fantastic. And I will be a part of this, the Chandrayaan-4, through this program. So we'll be in India for 2 weeks in Chennai. I hope to meet you in person or visit your institution also.
Ma'am, this is Dr. Kaveri, ma'am. Ma'am, I have a question. So when we test the reliability using SPSS and validity using the confirmatory factor analysis for a data set collected from the respondents, we may get good reliability values. For example, the Cornbox alpha value above 7.0 or whatever the something may be showing the data set is reliable. But with the same data set, when we are doing the confirmatory factor analysis, the items may not load properly on their factors, indicating the model is not valid. In such a situation, how we can refine our data set so that it becomes both reliable and valid?
Okay, so how can we refine our data or when? Can you repeat it because you're not
Ma'am,
audible?
with the same data set, ma'am, when we are going with reliability test by using the SPSS, we are getting the Cornbox alpha value above 7.0. But when you are doing the validity analysis, even the convergent and discriminant analysis, so you are not getting the proper value. The model does not fit. That means the items does not fit the factor or the construct. So what we can do, ma'am, to make our data set to have both reliability and validity?
Okay, thank you very much for this question.
This is the practical thing, practical struggle we are facing,
Yes.
ma'am. So with the data set, if the Cornbox value is above 7.0 and we are getting the proper correlation, regression, all the output is good. But the confirmatory factor analysis, the data set is something different. We couldn't able to get the proper discriminant validity as well as the convergent validity. So for that, we have to manipulate something that is not the true one. We are not supposed to do that, but to get the validity, we are doing that, ma'am. So how we have to refine our data set, ma'am?
Okay, so first, if validity reliability values are not proper, if your data shows low validity or low reliability, then you can refine the data using these steps. First, we improve, refine the data where Cornbox alpha is low. You check the item total correlation. So you look at the corrected item total correlation in SPSS. So items with values, below 0 to 3 should be considered for removal. Then you remove the item that decreases reliability. You use the table Cornbox alpha if item deleted. You remove items that increase when AI would delete it. You rerun the analysis. Then you check for reverse items. Sometimes negatively worded items need to be reverse coded. For example, you say, I'm unhappy most of the time. Reverse before calculating. Then you ensure that all items measure the same construct. Sometimes mixed items cause low reliability. If your construct, for example, is job satisfaction, don't mix items about salary, workload, or teamwork unless they belong to the same subdimension. Then another step is to increase number of items. A larger number of consistent items often increases reliability. And improve the quality of items. Improve the quality of items means clarify confusing wording and avoid double questions. For example, you say, I feel motivated and satisfied. So avoid this. How to improve validity now? Validity depends on how well the items measure the concept, right?
Yes.
So conduct factor analysis. Remove items that do not load on the correct factor. For the load, for example, is less than 0.4. Expert review, have experts check whether items accurately represent the concept. So what we call the content validity. And use validated, non-validated scales. Instead of making your own items, use existing scales from research. So example for workflow, if reliability is low, you can run the Cornbox alpha in SPSS. You look at item total correlation, then you remove poor performing items, you reverse code negative items, you rerun alpha, you perform factor analysis for validity, and you finalize the refined scale.
Okay. Ma'am, if possible, can you give one data set which shoots both the reliability and validity? Because it's very hard for me to do that, because yeah, for reliability, if the p-value is below 0.10, it is good. But for the opposite, for the validity, the p-value should be more than 0.05. So in such a case, the data is not properly fitting. So, will you please give one sample data set for that, ma'am, if possible?
Yes, of course. Yes, you meant that if your data set is considered reliable, if about mention it's more than the compact alpha, it's more than 0.70. The
Okay.
item total correlation is more than 0.30. The alpha, if item it improves, so if the leading item increases alpha, so the item means it's problematic. So the data set is reliable if most of items meet this criteria. Now, when the data is valid? A data set is considered valid if here Butler's test is significant. We have a p-value less than 0.05. The factor loadings also are bigger than 0.40, so items must load strongly on their factors. No high cross-loading, so an item should not load on multiple factors.
Okay.
AVE bigger than 0.50, you use a point factor analysis. So the data set is valid only when items load correctly and meet the statistical threshold. So I guess this is what I want to suggest. This is some strategies.
Okay, ma'am. Two of our participants have asked a question in the chat box. I'll just read. Ramu G have asked more informative session from Dr. RANIA. Okay, thank you for the wonderful effort. Okay, the question is reliability test versus factor analysis versus SEM, which is first, or best to construct a model and why? The first question.
Yes. So the simplest correct order and why each step comes first when we build a measurement model or a full structural model. We talk about, for example, social sciences and behavioral sciences. The correct order is we start by reliability testing first. What answers are my items internally consistent? Do they measure the same underlying construct? Why it comes first? Because if your items are not reliable, then doing factor analysis or structural equation model will produce misleading or unstable results. Reliability is the minimum requirement before exploring or confirming factor structure. What are the typical methods? Cronbach's, McDonald's item total correlations, corrected item total correlations, etc. Then we have factor analysis, which is done only after reliability because because you need to confirm that your items behave cohesively before interpreting latent structure. So first we have, for example, exploratory factor analysis, what it answers, how many factors exist, which items load on which factors, and why? Because exploratory factor analysis identifies the latent structure without imposing a predetermined model. Then, for example, confirmatory factor analysis. What answers does my hypothesized measurement model fit the data? Why? Because confirmatory factor analysis tests whether the factor structure discovered or hypothesized is valid or stable. And mention about, yes, structural equation model is last because this asks what are the relationship between the latent constructs, or does a structural model fit the data? Why it must come last? Because this requires reliable items, a validated measurement model from confirmatory factor analysis, clear constructs, and without this, any structural path coefficients are meaningless. So what is the recommended full workflow is first step reliability, check if each scale is internally consistent. Second step, the exploratory analysis. If the measure is new or adapted, explore the factor structure. Then confirmatory factor analysis, validate the factor structure from step 2, and step 4 is the structural equation modeling. So we test hypothesized relationships among the constructs. So the correct order is this: reliability, factor analysis, and structural equation modeling. Why? Because reliability is foundational. Factor structure must be validated before testing structural relationships, and structural equation modeling requires a sound measurement model. And this is the workflow.
Fine. Yeah, so hope Ramuji, the answer is being given by our today's resource person. And one more participant have asked, Suhas Ethel, who is our active participant, how do you define the item, total correlation, and what threshold do you usually use to decide that an item is very low or negative?
Okay, let's see this. Okay. Item total correlation actually measures how well each individual item on a scale correlates with the total score of the remaining items, excluding that item. So in other words, it shows whether an item is consistent with the overall construct the scale is trying to measure. So why it is important? Because if an item has a high item total correlation, it fits well with the other items. If an item has a low or negative item total correlation, it's not measuring the same thing as the rest of the scale. So this makes it a key diagnostic tool in reliability analysis. And you asked about the threshold. Okay, is item correlation low? More than 0.50, we have strong, very good item. From 0 to 30 to 0.49 is acceptable. 0.20, 0.29 is weak, so questionable. Less than 0.20 is very low, so we need to consider removing it. And negative, this means a serious problem, so we need to remove it immediately. So what to do if correlation is low or negative? If the item total correlation is less than 0.30, we review the item and we consider removing it. We check if it's reverse coded. If the item correlation is less than 0.20, then we talk about very weak item, which is usually removed because it reduces reliability. And if item total correlation is negative, then we talk about major red flag. This means that the item moves opposite to the construct. And this is usually caused by a poorly written item, a reverse worded item that was not reverse coded, and an item that belongs to a different factor. Negative items should be removed or corrected. So item total correlation shows how much an item correlates with the total score. Most researchers use 0.30 as a standard threshold. More than 0.30 is acceptable, less than 0.30 is low, and negative is invalid. This is my opinion.
Okay, ma'am. So thank you for answering the questions with clarity and patience. Ma'am, before we proceed to the final steps, we would like to quickly introduce our team to you.
Yes, of course.
So dear colleagues, may I request you all to please turn on your cameras when I call you by name and simply say hello to our resource person, or I'll just call your name and you please tell hi. You can also say or ask something to our resource
Thank you, ma'am.
person.
How energetic
Please
you are,
from
ma'am.
Greece. Okay, I'll now call, sorry, Dr. M. Kaveri.
Hello, ma'am.
Turn
Hello,
on your
ma'am.
camera.
Thank you for accepting our
Our
invitation.
convener,
The session is
a good
too
leader.
good, and you have covered so many things within an hour, ma'am. It's too hard to do. Thank you. Thanks a lot, ma'am.
Thank you.
And I now call, yeah, ma'am. WJS Julius Sudhir, ma'am, are you there? who is associate professor.
Ma'am is not there. I think so.
Julie Sudhir. Not there. Okay, fine. I'll call
Then I go.
Professor DG sir. Dhanagopal sir.
Hi,
Say
ma'am.
hi.
Hello, nice
Resource
to
person.
connect with all of
You are our
you.
faculty
Yeah,
members. Our department.
yeah, it was a nice session, ma'am.
I hope to meet you in person in India very soon.
Okay, so he is very polite and good person. Okay. Next, I'll call R. Bhavani ma'am. Dr. Bhavani ma'am, are you there? Hello, Bhavani ma'am. Kaveri,
Yes, Bhavani
Bhavani
ma'am
there?
is there,
Nice.
but
Good evening, ma'am. Good evening,
yes.
ma'am.
Good evening,
Hi
good
ma'am.
evening.
Nice to
You
see
can
you,
ask
ma'am.
any question. Who is from Greece?
Very interesting session, ma'am. Ma'am has clearly explained all the things. Thank you so much, ma'am.
Thank you, thank you.
Okay,
Welcome.
then okay. I'll call Dr. Vimal Devika. Vimal Devika, are you there?
Yes, Nirmala ma'am is there, ma.
Okay, I'll call. Okay, Nirmala ma'am, Dr. Nirmala Raghavan.
Very wonderful.
Ma'am, say hi.
Nirmala
Turn
ma'am.
Hello.
on your
Is
camera.
it not audible?
Yes, Nirmala ma'am.
Okay.
Kannan sir is there, ma.
Okay, then I'm Geeta, Dr. Geeta, who is recently completed her PhD successfully. Dr. Geeta is not here, I think. Okay, I'll call
Yes, ma'am. Yes, ma'am.
Kannan
Hi,
sir.
Geeta ma'am
ma'am.
is there. Geeta
Geeta,
ma'am.
hi.
Hi,
Say
ma'am.
hi.
How are you,
Hello,
ma'am?
hello. Hello. From
Good evening, ma'am.
Greece.
Yeah,
Ma'am,
Kannan.
she completed her PhD recently last month. A new graduate. Okay, Kannan sir.
Yes, ma'am.
Kannan sir. He is
Yes, ma'am.
our Tamil poet of our department. Tamil
Very, very
Pulavar.
important question
ஒரு
for the.
கவிதை. Okay. Then I now call.
Pratibha ma'am will go for a photo session, please.
Excited this session.
Yes,
Okay.
of course.
Too late.
But what's
Meena
more,
and Karthikeyan sir, please switch on your cameras, please. Karthikeyan
Karthikeyan
sir,
is
who
was
is
the one
behind
who
us.
Karthikeyan sir
coordinated
is
the whole thing. He
Karthikeyan sir, say
coordinated.
hi, sir.
Hello, ma'am.
Hello, thank you for
And it's me,
coordinating.
Pradeepa Nagarajan.
Thank
Hello,
you.
ma'am. Okay. He's techie of our department.
The
Okay, just to
participants, please
share
switch
it's
on your camera, please. Participants.
so. Dear participants, may I kindly request everyone, please switch on your cameras so that we will take a virtual program, and that too with a smile. Switch on- Is it over, sir? Karthikeyan, sir?
Yes, ma'am.
Thank you, ma'am.
Yeah, thank you.
Thank you.
So
Thank you, sir.
before we close, a gentle reminder to all the participants, the feedback link will be shared in the chat box. Please take a moment to fill it. It is required for participation and certification. And with that, so we come to the end of our today's session. A heartfelt thank you once again to our resource person, Dr. Raina, for sharing her knowledge, time, and valuable insights with us today. And thank you all the participants for your active participation and presence. We truly appreciate your commitment, especially today being a Sunday. Your consistent engagement is what makes this program meaningful and successful. Also, if your dinner tonight is dosa or idli with sambar or chutney, may it fuel the sweetest dreams. So you have a sleep well and recharge and get ready. It's Monday again tomorrow. This is Pradeepa Nagarajan signing off for
Ma'am,
the
vote of
evening.
thanks.
Have a pleasant, yeah.
Vote of thanks.
So I now request Nirmala ma'am to deliver vote of thanks. Ma'am, Nirmala ma'am, are you there?
Audible?
Yes, ma'am. Yeah, please continue.
Thank you. On behalf of sixth day
Ma'am, your
of our
voice
10th
is not.
international.
Ma'am, it's not audible.
It's not audible.
No, your voice is breaking, ma'am.
That's so.
Ma'am, better turn off your camera.
Just break it.
Okay.
Yes.
Am I audible?
Yes, right now, okay. Yes, continue, ma'am.
Am I audible, ma'am?
Yes, audible, ma'am. It's clear.
Okay. On behalf of the Department of Corporate Secretaryship, it gives me a great pleasure to deliver the vote of thanks for the 6th day of our 10th International Virtual Faculty Development Program on Research Methodology, Statistical Tools, and Structural Equation Modeling. First and foremost, I express our sincere gratitude to our respected dignitaries, Secretary Shri Udan Kumar Chodia, Associate Secretary Shri Hemant P. Chodia, Dean Dr. M.M. Ramya, Deputy Dean Dr. R. Sureka, and our Director Dr. N. Venkatramanan for their valuable support and the confidence they place in all our academic endeavors. A special and heartfelt word of appreciation to our esteemed resource person for today's session, Dr. RANIA, LAMPOU. Ma'am, your lecture on reliability, validity, and multivariate analysis was not only insightful but also beautifully structured. You took steps that often feel technical and heavy, yet you presented them with such clarity, depth, and real world relevance that every participant could follow with confidence. Your examples made the statistical ideas come alive, helping us to see how these tools shape strong and trustworthy research. The way you connected methodological thoroughness with practical application has truly strengthened our understanding and inspired us to approach our research with greater precision and purpose. I also extend my deepest thanks to all our faculty participants from various institutions whose active engagement, insightful questions, and enthusiasm make this FDP richer and more purposeful every single day. A sincere appreciation to Mr. B. Karthikeyan, who supported technically and worked tirelessly behind the scenes to ensure the smooth conduct of every session, and my special thanks to Ms. Pradeepa for her energetic comparing throughout the session that added life and warmth to our program. Once again, I extend my heartfelt thanks to everyone present here. Thank you. Thank you.
Thank you very much for
Thank
this
you,
wonderful
thank you,
opportunity.
ma'am.
Thank you. Thank you.
Thank you. And just to share from our side here in Chennai, the weather is little cloudy and we may receive rain later tonight. So it feels cool and calm here as well. So this is me, Pradeepa Nagarajan, signing off for this evening. Have a pleasant and peaceful night. And we look forward to seeing you in the upcoming session. Thank you. Take care. Thank you, ma'am.
Thank you, ma'am. Thanks a lot. Thank you, ma'am.
Thank you all. Take care.
Welcome. Bye.
Thank you. Thank you.
Thank you. Thank you.
Thank you.
Bye.